Hello there, and welcome to the Sleepy Science channel. Tonight we will be exploring the fascinating world of freezing, a phenomenon that shapes our planet, preserves our food, and creates some of nature's most stunning displays. From the microscopic dance of water molecules to the vast ice sheets covering Antarctica, freezing is both a simple process and an endlessly complex wonder. If you enjoy these quiet explorations, I invite you to like and subscribe or share a simple thought down in the comments. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is rest, settle in, and allow the calm of winter's embrace to carry you. Let's begin. The moment water becomes ice. Freezing is the transformation of liquid into solid. At its heart, freezing is a phase transition, the moment when molecules slow down enough to lock into place. For water, this happens at 0 degrees Celsius, under normal atmospheric pressure. But that simple number hides a world of complexity. Water molecules, in liquid form, are constantly moving, tumbling past each other in a chaotic dance. As temperature drops, they lose energy and slow down. Eventually, they arrange themselves into a crystalline lattice, a geometric pattern that repeats itself perfectly in all directions. This structure is ice, and it forms when the thermal energy can no longer overcome the attractive forces between molecules. The process begins with nucleation, the formation of the first tiny ice crystal. This can happen spontaneously if the water is cold enough, or it can be triggered by impurities, a speck of dust, a scratch on the container, or even vibrations. Once that first crystal forms, it becomes a template. Other water molecules attach to it, building the ice structure outward. The transformation spreads through the liquid like a growing web, sometimes slowly, sometimes in a sudden rush. To witness freezing is to watch order emerge from chaos. Molecules finding their places in a structure that will hold until warmth returns. Water expands when it freezes. Unlike most substances, water becomes less dense as it freezes. This unusual property has profound consequences for life on Earth. Most materials contract when they cool and solidify, their molecules packing more tightly together. Water does the opposite. As it freezes, the hydrogen bonds between molecules arrange themselves into a hexagonal lattice with open spaces between them. This structure takes up more volume than the same number of molecules in liquid form. The result is that ice is less dense than water, which is why it floats. This expansion can be powerful and destructive. Water seeping into cracks in rocks, roads, or buildings can freeze and exert tremendous force as it expands. Over time, this freeze-thaw cycle breaks down solid stone, carving valleys and shaping mountains. It shatters pipes in winter and cracks pavement into potholes. Ancient civilizations knew this force well, using it deliberately to split stones for construction. They would drill holes, fill them with water, and wait for winter's cold to do the work. The expansion of freezing water is gentle in its beginning but relentless in its power. Ice floats because of its crystal structure. The fact that ice floats is one of nature's most fortunate accidents. If ice were denser than water, it would sink to the bottom of lakes and oceans as it formed. Over time, bodies of water would freeze from the bottom up, trapping liquid water beneath a growing layer of ice. In winter, entire lakes would become solid blocks, and aquatic life would struggle to survive. But because ice floats, it forms a protective layer on the surface. This insulating cap slows further freezing, allowing liquid water to remain below even in the coldest climates. Fish, plants, and countless organisms shelter beneath the ice, waiting for spring. The crystal structure of ice is beautiful in its geometry. Each water molecule connects to 4 others through hydrogen bonds, forming a tetrahedral arrangement. These tetrahedrons link together into hexagonal rings, creating a lattice full of empty space. It is this spaciousness that makes ice less dense. The structure is not random, but follows precise mathematical rules, repeating itself in 6-fold symmetry. This is why snowflakes have 6 sides, and why ice crystals grow in such intricate patterns. The floating ice that crowns a winter pond is not just frozen water, but a testament to the elegant geometry hidden within simple molecules. Supercooled water can remain liquid below freezing. Water does not always freeze at 0 degrees Celsius. Under certain conditions, it can remain liquid well below its freezing point, a state known as supercooling. This happens when water is extremely pure and undisturbed, with no impurities or surfaces to trigger nucleation. The molecules are cold enough to freeze, but without a starting point, they remain in a metastable liquid state. Supercooled water is fragile. The slightest disturbance, a tap, a vibration, or the introduction of an ice crystal can trigger instant freezing. The transformation spreads rapidly through the liquid, sometimes in seconds. Supercooled droplets are common in clouds high in the atmosphere. Water vapor condenses into tiny droplets that can remain liquid even at temperatures of -20 degrees Celsius or colder. These droplets are hazardous to aircraft, as they can freeze instantly upon contact with metal surfaces, building up layers of ice that disrupt aerodynamics. In nature, supercooled clouds create freezing rain, a phenomenon where liquid rain freezes the moment it touches the ground, coating everything in a glassy shell of ice. To witness supercooled water freeze is to see a liquid remember, in an instant, that it should have been solid all along. Freezing preserves by halting decay. Humans have used freezing to preserve food for millennia. The principle is simple. Cold slows down the biological processes that cause food to spoil. Bacteria, molds, and enzymes all need warmth to function efficiently. As temperature drops, their activity decreases. At freezing temperatures, most microorganisms become dormant, unable to grow or reproduce. This does not kill them, but it suspends their activity, halting decay. Foods frozen quickly at very low temperatures can remain safe and nutritious for months or even years. The ancient peoples of cold climates were the first to discover this. Indigenous groups in the Arctic stored meat by burying it in snow or leaving it exposed to freezing winds. The food remained edible through long winters when fresh hunting was impossible. In the 18th century, explorers in polar regions observed that meat frozen in ice could be thawed and eaten without harm, even after decades. Today, modern freezers maintain temperatures well below 0, creating an environment where food remains in suspended animation. The carrots in your freezer are not truly preserved. They are paused, waiting for warmth to resume the processes that make them decay. Flash freezing locks in freshness. Not all freezing is equal. The speed at which something freezes determines the quality of preservation. Slow freezing allows large ice crystals to form inside cells, puncturing membranes and causing damage. When thawed, slowly frozen foods often become mushy and lose their texture. Flash freezing, by contrast, uses extremely cold temperatures, often -40 degrees Celsius or lower, to freeze items rapidly. This creates tiny ice crystals that do not rupture cell walls. The result is food that retains its structure, flavor, and nutritional value even after months in storage. The invention of flash freezing revolutionized the food industry. In the 1920s, Clarence Birdseye observed the Inuit people of Labrador using natural freezing to preserve fish. He noticed that fish frozen quickly in Arctic winds tasted fresher than those frozen slowly. Inspired, he developed machinery to replicate this rapid freezing commercially. His innovation made it possible to transport seafood, vegetables, and meats across great distances without spoilage. Today, flash freezing is used everywhere, from fishing boats that freeze their catch at sea to laboratories that preserve biological samples. It is a reminder that sometimes speed is the key to preservation. Cryonics freezes bodies in hope of future revival. Some believe that freezing can preserve not just food, but life itself. Cryonics is the practice of freezing human bodies, or brains, immediately after death, in the hope that future technology will be able to revive them. The process involves replacing blood with cryoprotective chemicals that prevent ice crystal formation, then cooling the body to temperatures below -130 degrees Celsius using liquid nitrogen. At these temperatures, all biological activity stops completely. Cells remain frozen in their final state, neither decaying nor aging. The science behind cryonics is controversial. Critics point out that current technology cannot reverse the freezing process without causing extensive damage. Ice crystals, even small ones, can disrupt delicate cellular structures, and the cryoprotective chemicals themselves may be toxic. There is no proven method to thaw a frozen body and restore life. Yet proponents argue that future advances in nanotechnology or medicine might make repair and revival possible. They see cryonics as a gamble, a way to preserve the possibility of life until science catches up. Whether it is hope or wishful thinking, cryonics represents humanity's desire to use freezing to cheat death itself. Ice cores reveal ancient climates. Ice holds more than water. In the polar regions, snow falls year after year, compressing into thick sheets of ice that trap bubbles of ancient air. These ice cores are time capsules, preserving a record of Earth's atmosphere stretching back hundreds of thousands of years. Scientists drill deep into glaciers and ice sheets, extracting long cylinders of ice that they analyze in laboratories. Each layer tells a story. The ratio of oxygen isotopes reveals past temperatures. Trapped air bubbles contain samples of the ancient atmosphere, showing levels of carbon dioxide and other gases. Dust and volcanic ash mark historic eruptions and changes in wind patterns. The deepest ice cores reach back more than 800,000 years, covering multiple ice ages and warm periods. By studying them, scientists have reconstructed Earth's climate history with remarkable precision. They can see how temperatures have fluctuated, how greenhouse gases have risen and fallen, and how the planet has responded to these changes. Ice cores revealed that carbon dioxide levels are higher now than at any point in the past 800,000 years. They show the tight link between greenhouse gases and global temperature. In the frozen layers of Antarctic ice, we find evidence of our planet's past and warnings for its future. Glaciers sculpt the landscape over millennia. Glaciers are rivers of ice, flowing slowly under their own weight. They form in places where more snow falls in winter than melts in summer. Over years, the snow compresses into ice, and the accumulation grows thick enough to begin moving. Glaciers carve the land as they flow, grinding down mountains, scouring valleys, and carrying rocks and soil. The ice acts like sandpaper, polishing bedrock and gouging out deep basins that become lakes when the ice retreats. The landscapes of much of North America and Europe were shaped by glaciers during the last ice age, which ended only about 11,000 years ago. The power of glacial erosion is immense. Glaciers can move boulders the size of houses, transporting them hundreds of kilometers from their origin. When the ice finally melts, these erratic boulders are left behind, perched incongruously on the landscape. Glacial valleys are U-shaped, carved by the slow, grinding passage of ice, while river valleys are V-shaped, cut by the faster flow of water. The fjords of Norway, the Great Lakes of North America, and the mountains of New Zealand all bear the marks of ancient glaciers. To look at these landscapes is to see the work of ice, patient and powerful, reshaping the surface of the Earth over thousands of years. Permafrost holds vast stores of carbon. In the Arctic and subarctic regions, much of the ground never thaws. This permanently frozen soil is called permafrost, and it extends hundreds of meters deep in some places. Permafrost forms where temperatures remain below freezing year-round, locking soil, rock, and organic matter in ice. Within this frozen ground lies a vast amount of carbon, the remains of plants and animals that died thousands of years ago. In warmer climates, this organic matter would decompose, releasing carbon dioxide into the atmosphere. But frozen, it remains preserved, locked away in ice. The concern now is that permafrost is beginning to thaw. As global temperatures rise, the frozen ground is warming, and in some areas, it is melting. When permafrost thaws, microbes become active again, breaking down the organic matter and releasing carbon dioxide and methane, both powerful greenhouse gases. The amount of carbon stored in permafrost is enormous, potentially twice as much as the entire atmosphere currently contains. If a significant portion of this permafrost melts, it could accelerate climate change dramatically. The frozen ground of the Arctic, once stable for millennia, is now a source of growing concern. Frost forms delicate patterns on cold surfaces. On cold mornings, windows and grass become canvases for frost. Frost is not frozen dew, but rather water vapor that transforms directly from gas to solid, a process called deposition. When surfaces cool below the freezing point and the air is humid, water molecules in the air lose energy and settle onto the cold surface as ice crystals. These crystals grow outward, forming intricate branching patterns that look like ferns, feathers, or trees. Each pattern is unique, shaped by the temperature, humidity, and microscopic texture of the surface. Frost appears most often on clear, calm nights when heat radiates away from surfaces into the sky. Car windows, blades of grass, and metal railings all become coated in delicate white ice. The patterns are not random, but follow the physics of crystal growth. Ice nucleates at certain points and branches outward in directions determined by the hexagonal structure of ice crystals. The result is beautiful and ephemeral, melting away as soon as the sun rises. To see frost on a window is to glimpse the hidden artistry of freezing, nature's temporary etchings on glass. Hoarfrost decorates trees with feathery ice. Hoarfrost is frost taken to an extreme. It forms on cold, foggy nights when water vapor in the air freezes directly onto surfaces, building up thick layers of ice crystals. Unlike regular frost, which forms thin coatings, hoarfrost grows outward into delicate needles and feathers. Trees covered in hoarfrost look like sculptures, every branch and twig outlined in white. The crystals can grow several centimeters long, creating a landscape that seems enchanted. Hoarfrost is most common in valleys and near bodies of water, where fog lingers and temperatures drop below freezing. The conditions must be just right: cold, calm, and saturated with moisture. When those conditions align, the result is breathtaking. Entire forests become frosted wonderlands, every surface coated in ice that sparkles in the weak winter sun. Hoarfrost is fragile, collapsing at the slightest touch or melting quickly when temperatures rise. To witness it is to see winter's most delicate artistry, a fleeting beauty that exists only in the coldest, stillest moments. Rime ice builds into fantastic shapes. Rime ice is another form of freezing fog, but it is denser and more durable than hoarfrost. It forms when supercooled droplets in fog or clouds freeze instantly upon contact with cold surfaces. Unlike hoarfrost, which grows slowly as vapor deposits, rime ice accumulates quickly as liquid droplets freeze on impact. The ice builds up into thick, rough coatings that can grow into bizarre shapes. On mountain peaks, rime ice creates formations that point into the wind, long spikes and ridges of ice, extending horizontally from rocks and structures. These ice formations can be enormous. On exposed summits, rime ice can coat towers, antennas, and weather stations in layers several meters thick. The ice is opaque and milky white, full of trapped air bubbles from the rapid freezing of droplets. It clings tenaciously to surfaces, sometimes persisting for days or weeks. In extreme cases, rime ice can add thousands of kilograms of weight to structures, enough to collapse towers or snap tree branches. Yet it is also beautiful, transforming ordinary landscapes into alien worlds. The spikes and ridges point like accusing fingers into the wind, frozen monuments to the power of freezing fog. Black ice forms, invisibly on roads. Not all ice is visible. Black ice is a thin, transparent layer of ice that forms on roads and pathways, nearly impossible to see. It earns its name because it is so clear that the dark pavement beneath shows through, making it look like wet road rather than ice. Black ice forms when temperatures drop just below freezing and moisture on the road surface freezes. It can also form from freezing rain or from water that seeps up through cracks and freezes on the surface. The ice is smooth and extremely slippery, offering almost no traction. Black ice is dangerous because it appears without warning. Drivers often do not realize they are on ice until their vehicle begins to slide. It forms most commonly on bridges, overpasses, and shaded areas where temperatures drop first. Even experienced drivers can be caught off guard. In winter, a stretch of road that looks perfectly safe can be covered in a glassy, invisible layer of ice. To encounter black ice is to be reminded that freezing can be subtle, hiding its presence until it reveals itself through loss of control. Glaciers flow like slow rivers. Glaciers may seem static, but they are constantly moving. Under the pressure of their own weight, ice behaves like a very thick fluid, flowing slowly downhill. The movement is imperceptible on human timescales, but it is real. Glaciers can flow anywhere from a few centimeters to several meters per day, depending on their size, slope, and temperature. The ice at the surface moves faster than the ice at the base, which is slowed by friction with the bedrock. This creates internal stresses, causing the ice to crack and form crevasses, deep fissures that can be deadly to anyone crossing a glacier. The flow of glaciers is driven by gravity. As snow accumulates at the top, the weight pushes the ice downward and outward. Where the glacier reaches warmer areas or the sea, the ice melts or breaks off into icebergs. This cycle of accumulation and loss determines whether a glacier is growing or shrinking. During ice ages, glaciers advanced, covering much of the northern continents. Today, most glaciers are retreating, losing ice faster than they gain it. To watch a glacier is to witness geology in motion, ice flowing like stone, reshaping the land grain by grain. Icebergs break from glaciers in dramatic calving events. When glaciers reach the sea, they do not stop. The ice flows out over the water, forming floating extensions called ice shelves. Eventually, the ice becomes unstable, and massive chunks break off in dramatic events called calving. These collapses can be sudden and violent. Sections of ice, the size of buildings, crack away from the glacier and crash into the ocean, sending waves surging outward. The sound is like thunder, echoing across the water. Calving events create icebergs, floating islands of ice that drift away from their parent glacier. Icebergs are massive and dangerous. Only about 10% of an iceberg's volume floats above water. The rest is hidden beneath the surface. This makes them hazardous to ships, which cannot always judge their true size. The Titanic's fatal encounter with an iceberg in 1912 remains one of history's most famous disasters, a reminder of the power of floating ice. Icebergs can drift for years, traveling thousands of kilometers from their origin. They melt slowly, eventually disappearing into the ocean. Each one is a fragment of a glacier, a piece of ice that once fell as snow on distant mountains, now adrift in the open sea. Icebergs can be blue, green, or striped. Icebergs are not always white. Some glow with a deep, luminous blue. Others show stripes of color, bands of white, blue, and even green running through the ice. These colors reveal the history frozen within. Blue ice forms when snow compresses so tightly that all air bubbles are squeezed out. Without air to scatter light, the ice absorbs red wavelengths and reflects blue, creating that striking azure color. The blue deepens with age and pressure, so the oldest, most compressed ice glows brightest. Green stripes in icebergs come from a different source. When glacial ice scrapes along the ocean floor or coastal rocks, it can pick up sediments, algae, or dissolved minerals. These materials freeze into the ice, tinting it green or brown. Some icebergs show complex patterns, layers of color stacked like geological strata. Each stripe is a moment in the ice's history, a record of where it traveled and what it encountered. To see a striped iceberg is to read its biography, written in bands of frozen time. The colors are subtle, often visible only in bright sunlight, but they transform ice from simple white to a palette of cold beauty. Pack ice forms when ocean water freezes. Ocean water freezes differently than fresh water. Because seawater contains salt, it freezes at a lower temperature, around -2 degrees Celsius. When the surface of the ocean cools enough, ice crystals begin to form. These crystals float and accumulate, gradually covering the surface with a layer of ice called pack ice. Unlike the solid ice of frozen lakes, pack ice is fragmented and dynamic. It consists of countless ice flows, pieces ranging from small chunks to vast sheets several kilometers across, all floating and jostling together. Pack ice expands and contracts with the seasons. In Arctic and Antarctic winters, it spreads across millions of square kilometers of ocean. In summer, much of it melts, retreating toward the poles. The ice is constantly in motion, pushed by winds and ocean currents. Flows collide and grind against each other, creating ridges and pressure points where the ice buckles upward. In some places, the ice is smooth and flat. In others, it is chaotic, a jumble of broken slabs piled atop one another. Pack ice provides crucial habitat for seals, polar bears, and other Arctic species, a frozen platform in an otherwise liquid world. Sea ice excludes salt as it freezes. When seawater freezes, something interesting happens. The ice that forms is mostly fresh water, not salty. As the ice crystals grow, they exclude salt molecules, pushing them into the surrounding liquid. This process is called brine rejection. The rejected salt increases the salinity of the water beneath the ice, making it denser and causing it to sink. This sinking water drives ocean circulation, contributing to the global conveyor belt of currents that regulates Earth's climate. Newly formed sea ice still contains pockets of concentrated brine trapped between ice crystals. Over time, these pockets drain away, and the ice becomes fresher. Old sea ice, several years old, is almost entirely fresh and can even be melted for drinking water. The exclusion of salt is why sea ice, despite forming in salt water, tastes much less salty than the ocean itself. This property has been crucial for Arctic explorers, who relied on melting old sea ice to obtain fresh water. The process of brine rejection is a reminder that freezing is selective, building structures that include some molecules and exclude others. Freezing rain coats everything in glass. Freezing rain is one of winter's most beautiful and hazardous phenomena. It occurs when rain falls through a layer of cold air near the ground and becomes supercooled, remaining liquid despite being below freezing. The moment these droplets touch any surface, they freeze instantly, coating everything in a smooth, glassy layer of ice. Trees, power lines, cars, and roads become encased in transparent ice that clings like a second skin. The weight of the ice can be immense. A single freezing rain storm can deposit several centimeters of ice, adding thousands of kilograms of weight to tree branches and power lines. The results can be catastrophic. Heavy ice snaps tree branches and brings down power lines, leaving communities without electricity for days or weeks. Roads become skating rinks, impassable and deadly. Yet there is undeniable beauty in the aftermath. Every surface gleams, encased in crystal. Sunlight refracts through the ice, creating dazzling displays of light. Forests become frozen sculptures, each twig and leaf preserved in glass. The beauty is temporary, lasting only until temperatures rise or the weight becomes too great and everything shatters. Freezing rain is nature's glasswork, fragile and dangerous in equal measure. Ice storms transform landscapes into crystal worlds. When freezing rain persists for hours, it creates an ice storm. These events are among the most destructive winter weather phenomena. Ice accumulates layer upon layer, coating everything in thickening shells. The weight becomes unbearable. Trees bow under the load, their branches cracking and falling. Power lines sag and snap. Buildings groan under ice-covered roofs. The soundscape of an ice storm is unforgettable. The constant tinkling of falling ice, the sharp crack of breaking branches, the distant crash of collapsing structures. Yet for those safe indoors, the aftermath of an ice storm is a winter wonderland like no other. The world becomes a sculpture garden of ice. Every surface sparkles. Grass blades stand frozen in place, encased individually. Fences look like they are made of glass. When sunlight breaks through the clouds, the landscape blazes with reflected light, almost too bright to look at. Walking through an ice-covered forest is otherworldly, as if stepping into a fairy tale. But the beauty comes at a cost. Recovery from severe ice storms can take weeks, and the ecological damage persists for years. Trees stressed by ice breakage are more vulnerable to disease and insects. The frozen beauty is real, but so is the destruction hidden beneath. Frost heave pushes rocks to the surface. In regions with cold winters, gardeners and farmers notice something strange. Rocks seem to rise from the ground, appearing in fields that were cleared the previous year. This is caused by frost heave, a process where freezing ground lifts objects upward. When water in the soil freezes, it expands, creating pressure that pushes everything upward. As the ice melts in spring, soil particles fall back down, but rocks and other objects remain slightly elevated. Over multiple freeze-thaw cycles, rocks gradually migrate to the surface. Frost heave affects more than rocks. It damages roads, cracking pavement and creating potholes. It can lift fence posts, shift building foundations, and disrupt underground pipes. In Arctic regions, frost heave creates strange patterns in the landscape, sorting stones into circles, polygons, and stripes. These patterned ground formations are purely natural, created by the repeated freezing and thawing of soil. To see a field where stones have been pushed up by frost is to witness the slow but relentless power of ice, working invisibly beneath the surface, rearranging the very ground we walk on. Cryovolcanoes erupt ice instead of lava on distant moons and icy worlds. Volcanoes erupt not with molten rock, but with water, ammonia, and methane. These are cryovolcanoes, also called ice volcanoes, and they exist on moons like Enceladus, Triton, and Europa. The mechanism is similar to Earth's volcanoes. Heat from below forces material upward through cracks in the crust. But instead of lava, the erupting material is liquid or slushy ice, sometimes mixed with gases. When it reaches the frigid surface, it freezes instantly, building up mountains and flows of ice. Enceladus, a moon of Saturn, has active cryovolcanoes that shoot plumes of water vapor and ice particles hundreds of kilometers into space. These plumes were discovered by the Cassini spacecraft and revealed that Enceladus has a subsurface ocean, kept liquid by tidal heating. The erupting material forms a ring around Saturn, made entirely of ice. On Triton, Neptune's largest moon, cryovolcanoes erupt nitrogen gas, creating geysers that darken the surface with deposited material. Cryovolcanoes are a reminder that ice is not always inert. Under the right conditions, it can flow, erupt, and reshape landscapes, just like molten rock does on Earth. Frost quakes crack like thunder in deep cold. In the coldest winter nights, the ground itself can crack with a sound like an explosion. These events are called frost quakes or cryosisms, and they occur when water trapped in soil or rock freezes rapidly. The ice expands with tremendous force, building up pressure until the ground fractures suddenly. The cracking releases energy as a sharp boom or series of booms, loud enough to wake people from sleep and rattle windows. The ground may even shake slightly, though not from an earthquake. Frost quakes are most common during extreme cold snaps when temperatures plunge rapidly. They tend to occur in the middle of the night when the ground is coldest. People who experience them often describe the sound as a gunshot, an explosion, or a heavy object falling. Sometimes houses crack and creak as frost heaves shift foundations. Frost quakes are harmless, releasing tension in the frozen ground, but they are startling. They are a reminder that ice exerts force, and when that force becomes too great, something must give. The earth itself cracks under the pressure of freezing. Needle ice lifts soil into delicate columns. On cold mornings in damp soil, you may encounter a strange phenomenon. The ground is covered with thin columns of ice, each topped with a small pebble or clod of soil. This is needle ice, formed when water in the soil freezes from the surface downward. As the ice crystals grow upward, they lift the soil particles above them, creating pillars that can be several centimeters tall. The result looks like a tiny forest of ice needles, each one supporting its small burden. Needle ice forms best when temperatures hover just below freezing, and the soil is moist but not saturated. It is fragile, collapsing at the slightest touch, or melting quickly once the sun rises. Walking on ground covered in needle ice produces a satisfying crunching sound as the delicate structures collapse underfoot. Needle ice plays a role in soil erosion, lifting particles that are then more easily washed away by rain or wind. It is a small-scale process, but over many freeze-thaw cycles, it contributes to shaping the landscape. To find needle ice is to discover one of winter's smallest wonders. intricate, and ephemeral. Anchor ice forms on river and lake bottoms. Ice does not always float. Under certain conditions, it can form underwater, attached to rocks, plants, and the riverbed itself. This is called anchor ice or bottom ice, and it forms when water is supercooled, remaining liquid below freezing. The flowing water loses heat to the cold air above faster than it can freeze, creating a layer of supercooled water. When this water contacts solid surfaces, it freezes instantly, forming ice underwater. Anchor ice can grow thick enough to lift rocks and boulders, carrying them downstream when the ice eventually breaks free. It affects aquatic life, trapping fish and insects in ice or disrupting their habitats. In rivers, anchor ice can choke flow, causing water levels to rise unexpectedly. It is most common in fast-flowing, shallow streams on extremely cold nights. Divers exploring under ice have reported forests of anchor ice, icy structures growing upward from the bottom like inverted icicles. Anchor ice is a hidden aspect of freezing, occurring out of sight beneath the surface, yet affecting the entire aquatic ecosystem. Frazil ice forms as tiny crystals in turbulent water. In cold, turbulent rivers and oceans, ice can form as a suspension of tiny crystals called Frazil ice. These crystals are small, needle-like or disc-shaped, and they form when water is supercooled and agitated. The turbulence prevents the crystals from joining together into solid ice, so they remain dispersed throughout the water, giving it a milky or slushy appearance. Frazil ice can accumulate in enormous quantities, clogging water intakes for power plants and disrupting shipping. When Frazil ice accumulates, it can congeal into larger masses called ice dams, which block rivers and cause flooding. The formation of Frazil ice is noisy, the crystals scraping against each other and against solid surfaces with a distinctive hissing or rustling sound. In polar seas, Frazil ice is the first stage of sea ice formation, the crystals eventually aggregating into pancake ice and then solid pack ice. To see a river filled with Frazil ice is to watch water caught in the act of freezing, unable to solidify fully because of constant motion, suspended between liquid and solid. Pancake ice forms rounded flows in rough seas. In cold, wave-tossed oceans, ice forms in a unique way. Small ice crystals grow and collide with each other, their edges gradually rounding from repeated impacts with waves and other ice. The result is pancake ice, circular flows with raised edges, looking remarkably like stacks of frozen pancakes floating on the sea. These flows can range from a few centimeters to several meters in diameter. They bob and jostle in the waves, clinking against each other with a sound like wind chimes. Pancake ice is common in the polar seas during autumn and early winter, when ice is just beginning to form, but the ocean is still rough with waves. As temperatures drop further, the pancakes freeze together, forming larger sheets of pack ice, but during their formation, they create a surreal seascape, a field of circular ice flows, stretching to the horizon. To witness pancake ice is to see ice adapting to its environment, shaped by waves into forms that seem almost deliberate. Nature has no shortage of creativity, even in something as simple as freezing water. Ice spikes form on freezing water surfaces. Sometimes, as water freezes in a tray or container, a strange structure forms, a spike of ice rising vertically from the surface. Ice spikes are rare and unexpected, resembling tiny stalagmites or inverted icicles. They form when water expands as it freezes, but the surface freezes first, trapping liquid water beneath. Pressure builds, and the liquid is forced upward through a small opening in the ice. As it rises, it freezes, building the spike upward. The process continues until the water runs out or the spike becomes unstable and collapses. Ice spikes are most common when freezing distilled or purified water, which lacks impurities that would otherwise create nucleation sites. They are delicate and often break before they can be observed. Their formation is not fully understood, and even small changes in conditions can prevent them from forming. To find an ice spike in your freezer is to discover a small mystery, an accidental sculpture created by the physics of freezing. They serve no purpose, yet their existence is a reminder that even familiar processes can produce the unexpected. Snowflakes form from water vapor, freezing directly. Snow is not frozen rain. It forms high in the atmosphere when water vapor transitions directly to ice, skipping the liquid phase entirely. This process is called deposition, and it occurs around a tiny nucleus, a speck of dust, pollen, or even a bacterium. The ice crystal that forms is microscopic at first, but as it falls through clouds rich with water vapor, more vapor deposits onto it, building the crystal outward. The shape the crystal takes depends on temperature and humidity. At different conditions, crystals grow as plates, columns, needles, or dendrites, the classic six-sided snowflakes. No two snowflakes are exactly alike, a statement often repeated but essentially true. The path each crystal takes through the atmosphere is unique, exposing it to slightly different conditions of temperature and humidity. These variations affect how and where new ice deposits, creating intricate patterns that differ from crystal to crystal. Some snowflakes are simple, hexagonal plates with little detail. Others are breathtakingly complex, with elaborate branching arms covered in fine details. The variety is endless, each snowflake a unique expression of the physics of crystal growth. Snowflakes are always six-sided. Despite their infinite variety, all snowflakes share one feature: six-fold symmetry. This is not coincidence, but a direct result of the molecular structure of ice. Water molecules bond in hexagonal arrangements, and, as ice crystals grow, they follow this underlying geometry. The crystal develops six branches, or sides, extending outward from the center. The pattern repeats at every scale, from the overall shape down to the smallest details. Even when snowflakes are irregular or broken, the six-fold symmetry is usually evident. The discovery of snowflake symmetry dates back centuries. In the early 1600s, Johannes Kepler pondered why snowflakes always had six sides, writing an essay on the subject. He correctly intuited that the shape must arise from some inherent property of water. Centuries later, scientists confirmed that the hexagonal structure of ice crystals dictates the six-sided symmetry of snowflakes. It is a beautiful example of how microscopic structure determines macroscopic form. To hold a snowflake and see its six arms is to glimpse the hidden geometry of water molecules, arranged in a pattern that has existed since the beginning of ice itself. Wilson Bentley photographed thousands of snowflakes. In the late 1800s, a Vermont farmer named Wilson Bentley became fascinated by snowflakes. Using a microscope attached to a camera, he spent decades photographing individual crystals. His images revealed for the first time the stunning complexity and variety of snowflakes. He captured thousands of photographs, each showing intricate patterns and delicate structures invisible to the naked eye. His work proved that no two snowflakes are identical and revealed the mathematical beauty hidden in these tiny ice crystals. Bentley worked in bitter cold, rushing to photograph snowflakes before they melted. He mounted crystals on black velvet and worked quickly, capturing images on glass plates. His dedication was extraordinary, spending winters outside in freezing conditions to document these ephemeral forms. His photographs became famous worldwide, appearing in books and exhibitions. Today, Bentley is known as Snowflake Bentley, the man who first showed the world the hidden artistry of winter. His legacy is a collection of images that remain stunning more than a century later, proof that beauty exists at every scale, even in something as fleeting as a snowflake. Thundersnow combines snowfall with lightning. Thunder and lightning are usually associated with summer storms, but occasionally they occur during snowstorms. This phenomenon is called thundersnow, and it is rare and striking. Thundersnow requires the same ingredients as a regular thunderstorm: instability in the atmosphere, moisture, and lift. But it occurs in winter conditions, when precipitation falls as snow rather than rain. The lightning during thundersnow can be spectacular, illuminating falling snow with sudden flashes of light. The thunder is often muffled by the snow, sounding deeper and less sharp than summer thunder. Thundersnow is most common near large bodies of water, where cold air moving over warmer water creates instability. It can also occur along weather fronts, where warm and cold air collide violently. Forecasters sometimes struggle to predict thundersnow because the conditions that create it are delicate and short-lived. For those who witness it, thundersnow is unforgettable, the world blanketed in white, silent except for the muffled rumble of thunder and the sudden strobe of lightning. It is a reminder that storms can occur even in the coldest conditions, that the atmosphere never truly rests. Lake effect: snow creates enormous, localized snowfalls. In late autumn and early winter, cold air masses sometimes sweep across large lakes. As the air moves over the relatively warm water, it picks up moisture and heat. When this modified air reaches the far shore, it rises, cools, and dumps its moisture as snow. This is called lake effect snow, and it can produce staggering amounts of snowfall in very localized areas. Regions downwind of the Great Lakes in North America are famous for lake effect snow, which can bury towns in meters of snow within days. Lake effect snow is highly localized. One town may receive almost no snow, while another, just a few kilometers away, is buried. The bands of snow are narrow, determined by wind direction and the shape of the lake. Forecasting lake effect snow is challenging because small changes in wind direction can shift the bands dramatically. For residents of lake effect snow zones, winter means preparing for sudden, intense snowfalls that can shut down roads and isolate communities. It is a reminder that lakes influence climate, storing heat in summer and releasing it in winter, shaping weather patterns for hundreds of kilometers downwind. Blizzards combine snow and wind into whiteouts. A blizzard is more than just heavy snow. It is a combination of snow, strong winds, and low visibility that creates dangerous conditions. The official definition varies by country, but typically a blizzard requires sustained winds of at least 55 kilometers per hour, visibility reduced to less than 400 meters, and conditions lasting for at least 3 hours. The snow itself may be falling from the sky, or it may be snow already on the ground, being lifted and blown by the wind. Either way, the result is a whiteout, a disorienting wall of white, where sky and ground blend together. In a blizzard, travel becomes nearly impossible. Roads disappear beneath drifting snow. Landmarks vanish in the swirling white. People caught outside can become disoriented and lost within meters of shelter. Blizzards can last for days, burying entire towns and stranding communities. The wind chill can be life-threatening, freezing exposed skin in minutes. Yet for those safely indoors, the sound of a blizzard has a strange, almost hypnotic quality. The roar of wind, the hiss of snow against windows, the deep quiet that follows when it finally stops. Blizzards are nature's reminder of its power. Winter, unleashed in its most primal form. Snowdrifts form, complex sculptures. Even after the snow stops falling, wind continues to shape it. Snowdrifts form where wind deposits snow in the lee of obstacles, buildings, fences, trees, or terrain features. The wind carves the snow into smooth curves and sharp edges, creating sculptures that can be several meters tall. The physics of snowdrift formation is complex, involving the interaction of wind, topography, and snow properties. Engineers study drifts to design buildings and roads that minimize snow accumulation. Snowdrifts can be both beautiful and problematic. They create smooth, wave-like patterns across open fields, resembling frozen ocean waves. But they also block roads, bury vehicles, and collapse under their own weight, sometimes trapping people or animals. The shapes of drifts are never random. They follow aerodynamic principles, the same forces that shape sand dunes in deserts. Cornices, overhanging snow formations on ridges and cliffs, are particularly dangerous. They appear solid, but are often hollow underneath, and they can collapse without warning. To see a field of snowdrifts is to witness wind made visible, its invisible currents written in white across the landscape. Sastrugi are wind-carved snow ridges. In polar regions and high mountains, wind carves snow into sharp ridges called sastrugi. These formations are parallel ridges and grooves, often several meters long and up to a meter tall, oriented perpendicular to the prevailing wind. Sastrugi form when wind erodes softer snow and deposits harder snow, creating a washboard-like surface. The ridges are hard and icy, difficult to walk on or drive across. They make polar travel challenging, as vehicles and sleds must navigate the uneven terrain. Sastrugi are most common in areas with strong, consistent winds and relatively little new snowfall. Antarctica is covered with vast fields of sastrugi, their parallel lines stretching for kilometers. The ridges can be sharp enough to cut through fabric and wear down sled runners. For explorers, sastrugi are an exhausting obstacle, forcing slow, jarring travel. Yet they are also beautiful in their stark geometry, patterns carved by invisible forces, proof of wind's relentless power to shape even the hardest snow. Snowpack consists of many layers with different properties. A snow-covered mountain slope may look uniform, but beneath the surface, the snowpack is complex. It consists of multiple layers, each deposited during different storms and transformed by temperature, wind, and time. Some layers are soft and fluffy, others hard and icy. Some are thick, others thin. The interfaces between layers can be weak, creating zones where the snowpack is prone to failure. Understanding snowpack structure is crucial for avalanche forecasting. Snow scientists dig pits into the snowpack and examine each layer, measuring grain size, hardness, and temperature. They look for weak layers, often composed of faceted crystals or depth hoar, which can collapse under stress. These weak layers are where avalanches often initiate. The snowpack is dynamic, constantly changing as snow settles, melts, and refreezes. Temperatures cycling above and below freezing transform snow grains, sometimes strengthening layers, sometimes weakening them. To understand snow is to understand that it is not static, but alive with internal processes, evolving day by day beneath its white surface. Avalanches release when snowpack fails. An avalanche is a sudden, rapid flow of snow down a slope. It occurs when the stresses within the snowpack exceed the strength of the snow. The trigger can be additional weight from new snow, a person walking on the slope, or even a loud sound creating vibrations. Once started, an avalanche can accelerate to speeds over 200 kilometers per hour, carrying thousands of tons of snow. The power is immense, capable of snapping trees, flattening buildings, and burying anything in its path. Avalanches are classified by type. Loose snow avalanches start at a point and fan outward as they descend, like a river of snow. Slab avalanches occur when an entire layer of cohesive snow breaks free and slides as a unit. Slab avalanches are more dangerous because they can release without warning and involve much larger volumes of snow. The sound of an avalanche is unforgettable, a deep rumble that builds to a roar, the ground shaking as tons of snow rush past. For skiers, snowboarders, and climbers, avalanches are a constant danger, one that requires knowledge, caution, and respect. Snow insulates, protecting life beneath. Snow may seem cold, but it is actually an excellent insulator. The air trapped between snow crystals reduces heat transfer, creating a blanket that protects the ground and anything beneath it. In winter, the soil under deep snow often remains warmer than the air above, sometimes just below freezing, even when air temperatures plunge far lower. This insulation allows plants and animals to survive harsh winters. Small mammals, like voles and shrews, live in the subnivean zone, the space between the ground and the snow, where temperatures are relatively stable. In some ecosystems, deep snow is essential for survival. Without it, soil freezes deeply, killing plant roots. Shallow snow means exposure to bitter cold, threatening hibernating animals and overwintering insects. The insulating properties of snow depend on its structure. Light, fluffy snow traps more air and insulates better. Dense, icy snow conducts heat more readily and provides less protection. To see a snow-covered landscape is to see a blanket that moderates extremes, protecting life through the coldest months until spring returns. Igloos use snow's insulating properties. The Inuit peoples of the Arctic developed an ingenious shelter from the materials at hand: snow and ice. An igloo is a dome-shaped structure built from blocks of compacted snow. The design is remarkably efficient. The dome shape distributes weight evenly, preventing collapse, while the thick snow walls provide excellent insulation. Inside an igloo, body heat and a small lamp can raise temperatures to comfortable levels, even when outside temperatures are far below freezing. Building an igloo requires skill and knowledge. The snow must be the right consistency, dense enough to cut into blocks, but not so hard that it cannot be shaped. Blocks are arranged in a spiral, leaning inward to form the dome. Gaps are filled with loose snow, and the inside surface is often smoothed and allowed to glaze with ice, further improving insulation. An igloo can be surprisingly warm, with interior temperatures around 0 degrees Celsius or higher, a stark contrast to the negative 30 or 40 degrees outside. The igloo is a testament to human ingenuity, using the properties of frozen water to create shelter in one of Earth's harshest environments. Frost flowers bloom on new sea ice. In the polar oceans, newly formed sea ice sometimes sprouts delicate structures that look like flowers. These are frost flowers, intricate formations of ice crystals that grow upward from the ice surface. They form when extremely cold air moves over new, thin ice. Water vapor evaporates from the ice or from cracks in the surface and immediately freezes, depositing as crystals that build upward in feathery, flower-like shapes. Frost flowers can grow several centimeters tall and are incredibly fragile. Frost flowers are beautiful, but they also have scientific importance. They contain high concentrations of salt, rejected from the ice as it formed. They also contain organic compounds and can host microbial life. When winds break them apart, the fragments become aerosols that can travel thousands of kilometers, potentially affecting cloud formation and atmospheric chemistry. Frost flowers are ephemeral, lasting only hours to days before wind or warmer temperatures destroy them. To see a field of frost flowers on new sea ice is to witness one of winter's most delicate and fleeting creations. Ice caves form within glaciers. Inside glaciers, water sometimes carves passages and chambers, creating ice caves. These caves form when meltwater streams tunnel through or beneath the ice, eroding away material and leaving hollow spaces. Ice caves are dynamic, changing constantly as glaciers flow and melt. They can be vast, with chambers large enough to hold hundreds of people, or they can be narrow, winding passages barely wide enough to squeeze through. The walls are smooth ice, glowing blue when light penetrates. Exploring ice caves is hazardous. They can collapse without warning, and glacial movement can close passages or open new crevasses. Despite the dangers, ice caves attract adventurers and photographers, drawn by their otherworldly beauty. Light filtering through ice takes on a surreal blue glow, and the shapes carved by water are organic and flowing. Some ice caves have frozen waterfalls inside them, where streams froze mid-flow, creating curtains and pillars of ice. To walk inside a glacier is to enter a hidden world, a place where ice is not static but alive, shaped by forces both delicate and immense. Permafrost can preserve ancient life. When animals and plants die in permafrost regions, they sometimes freeze before they can decay. The cold halts decomposition, preserving them for millennia. Woolly mammoths, extinct for thousands of years, have been found frozen in Siberian permafrost, their flesh so well preserved that scientists could examine stomach contents and analyze DNA. Frozen carcasses of other Ice Age animals, bison, horses, and lions, have also been discovered, offering insights into life during the last glacial period. These discoveries are scientifically invaluable. They provide information about extinct species that skeletons alone cannot offer: what they ate, how their bodies were structured, even what they looked like. Some mammoth carcasses still have hair and skin intact. Plants frozen in permafrost can be thousands of years old yet still recognizable. In some cases, seeds frozen for millennia have been successfully germinated, bringing ancient plants back to life. Permafrost is a time capsule, preserving fragments of the past in frozen suspension, waiting to be rediscovered. Cryonics companies store bodies in liquid nitrogen. Several companies offer cryonic preservation, freezing deceased individuals in the hope that future technology will revive them. After legal death, the body is cooled and blood is replaced with cryoprotectant chemicals. The body is then gradually cooled to the temperature of liquid nitrogen, around -196 degrees Celsius. At this temperature, all biological activity stops. Cells are frozen, suspended between life and death. The bodies are stored in insulated tanks filled with liquid nitrogen, which must be replenished regularly. The entire process is controversial. Medical professionals point out that current freezing techniques cause significant cellular damage, and no technology exists to reverse it. Legal and ethical questions abound. Who owns the bodies? What happens if the company goes bankrupt? Despite these concerns, hundreds of people have been preserved, and many more have signed up for the procedure upon death. They gamble that future science will solve problems that seem insurmountable today. Whether cryonics is visionary or futile remains unknown. For now, the frozen wait, suspended in hope. Frozen organs can be transplanted. Cryopreservation is not limited to entire bodies. Human cells, tissues, and even some organs can be frozen and later thawed for medical use. Sperm, eggs, and embryos are routinely frozen for fertility treatments. Blood and bone marrow can be frozen and stored for transfusions and transplants. The key is using cryoprotective agents, chemicals that prevent ice crystals from forming inside cells. Without these agents, freezing ruptures cell membranes and kills the tissue. Freezing larger organs, like hearts and kidneys, remains challenging. Organs are complex structures, and ensuring every part freezes uniformly without damage is difficult. Researchers are developing new techniques, including vitrification, which cools tissues so rapidly that water forms a glass-like solid rather than ice crystals. Success would revolutionize transplant medicine, allowing organs to be stored for long periods rather than the current few hours. The goal is to freeze organs without harm, suspending them until needed. It is a frontier where medicine meets the science of freezing, with the potential to save countless lives. Frozen embryos have been stored for decades. Human embryos, created through in vitro fertilization, can be frozen and stored for years, even decades. The process, called cryopreservation, involves cooling embryos to very low temperatures using cryoprotectants to prevent ice damage. These embryos remain viable, and when thawed, they can be implanted and develop into healthy babies. Some people have given birth to children from embryos that were frozen for more than 20 years. This technology raises complex ethical and social questions. Embryos can outlive their biological parents. Families must decide what to do with frozen embryos if they no longer want children. Some donate them to other couples, others to research, and some choose to discard them. The ability to freeze time, in a sense, creates situations that previous generations never faced. Yet the technology is also a gift, allowing people to preserve their fertility, delay childbearing, and overcome medical challenges. Frozen embryos are potential lives, suspended in cold storage, waiting for the moment they might be thawed and given the chance to grow. Some animals can survive being frozen solid. Most animals die if their body fluids freeze, but a few have evolved remarkable adaptations to survive freezing. Wood frogs, for example, can endure having up to 70% of their body water turn to ice. When temperatures drop below freezing, glucose floods their cells, acting as a natural antifreeze that prevents ice crystals from forming inside cells. Ice forms in spaces between cells and organs instead, where it causes less damage. The frog's heart stops beating, breathing ceases, and it appears dead. But when temperatures rise, the ice melts, and the frog thaws and revives. Other animals with similar abilities include certain turtles, insects, and snails. Arctic ground squirrels lower their body temperature to below freezing without freezing solid, a state called supercooling. Some insects produce antifreeze proteins that bind to ice crystals and prevent them from growing. These adaptations are extraordinary examples of evolution solving the problem of cold. To survive winter, these animals essentially die and are reborn with each freeze-thaw cycle, their bodies shutting down and restarting in rhythm with the seasons. Tardigrades can survive extreme freezing. Tardigrades, also called water bears, are microscopic animals renowned for their resilience. They can survive conditions that would kill almost any other organism, including extreme freezing. When faced with harsh conditions, tardigrades enter a state called cryptobiosis, where their metabolism nearly stops. They expel most of their body water and curl into a ton, a dormant, desiccated form. In this state, they can endure temperatures as low as -273 degrees Celsius, just above absolute zero. Tardigrades have been frozen for years and revived successfully. They have survived in the vacuum of space and at pressures 6 times greater than the deepest ocean trenches. Their ability to withstand freezing comes from special proteins that protect their cells and DNA from damage. When conditions improve, they rehydrate and resume normal life. Tardigrades are proof that life can be far more resilient than we imagine, capable of enduring extremes that seem incompatible with biology. They are microscopic survivors, thriving in niches where almost nothing else can. Cryotherapy uses extreme cold for health benefits. Cryotherapy involves exposing the body to extremely cold temperatures for short periods, typically 2 to 4 minutes. People enter chambers cooled to -110 degrees Celsius or colder, often using liquid nitrogen vapor. Proponents claim it reduces inflammation, speeds recovery from exercise, improves mood, and alleviates pain. The extreme cold triggers physiological responses. Blood vessels constrict, then dilate when you warm up, potentially flushing toxins and delivering fresh oxygen to tissues. The scientific evidence for cryotherapy is mixed. Some studies suggest benefits for muscle recovery and inflammation, while others find little effect beyond placebo. The practice is popular among athletes, who use it to recover between training sessions. Whole-body cryotherapy is different from localized cryotherapy, where cold is applied to specific injuries, a treatment with stronger scientific support. Despite uncertainties, cryotherapy chambers have become common in spas and wellness centers. The experience is intense. The air is so cold it stings, breath comes in gasps, and time seems to slow. Whether the benefits are real or perceived, the cold is undeniably shocking. Freeze-drying removes water while preserving structure. Freeze-drying, or lyophilization, is a preservation method that removes water from frozen material through sublimation. The process starts by freezing the material, then placing it in a vacuum. Under low pressure, ice sublimes directly from solid to vapor without melting. The result is a dry, lightweight product that retains its structure and can be stored for years without refrigeration. When water is added back, the material rehydrates, often returning close to its original form. Freeze-drying is used extensively for food, especially for camping meals, military rations, and instant coffee. It preserves nutrients better than heat drying, which can destroy vitamins and proteins. Pharmaceuticals are often freeze-dried for stability, allowing vaccines and medicines to be stored and transported more easily. Freeze-dried flowers and even entire animals are used in museum displays. The process is slow and energy-intensive, but it produces results that other preservation methods cannot match. To hold a freeze-dried strawberry is to hold fruit that has been transformed, its water replaced by air, yet its structure intact. Absolute zero is the coldest possible temperature. Temperature measures the average kinetic energy of particles. The colder something is, the slower its particles move. Absolute zero, -273.15 degrees Celsius, or 0 Kelvin, is the temperature at which particles theoretically stop moving entirely. It represents a fundamental limit. Temperatures cannot go lower because there is no slower motion than none. Absolute zero is a concept from thermodynamics, the point where entropy reaches its minimum. In practice, absolute zero cannot be reached. The third law of thermodynamics states that as temperature approaches absolute zero, the amount of energy required to remove additional heat increases infinitely. Scientists have cooled materials to within billionths of a degree of absolute zero, but never to the limit itself. At these extreme temperatures, matter behaves strangely. Helium becomes a superfluid, flowing without friction. Quantum effects dominate, and classical physics breaks down. Absolute zero is not just cold, it is the boundary where the rules of nature change. Liquid nitrogen boils at extremely low temperatures. Liquid nitrogen is nitrogen cooled below -196 degrees Celsius. its boiling point. At room temperature, nitrogen is a gas, making up 78% of Earth's atmosphere. But when cooled sufficiently, it condenses into a clear, colorless liquid. Liquid nitrogen is extremely cold and boils vigorously when exposed to warmer temperatures, producing clouds of nitrogen gas. It is used widely in laboratories, medicine, and industry for rapid freezing and cooling. One common demonstration involves dipping objects into liquid nitrogen. Flowers become brittle and shatter like glass. Rubber balls bounce higher because the material becomes harder. Bananas can be used as hammers. The transformations are dramatic and instant. Liquid nitrogen is also used to freeze warts and other skin lesions in medical procedures. The extreme cold kills cells on contact. Handling liquid nitrogen requires caution, as it can cause severe frostbite in seconds. Yet its utility is undeniable, a tool that brings the deep cold of space into everyday use. Helium becomes a superfluid when extremely cold. When helium is cooled to temperatures near absolute zero, it undergoes a bizarre transformation. Below 2.17 Kelvin, helium becomes a superfluid, a state of matter with zero viscosity. Superfluid helium flows without friction, defying normal fluid behavior. It can climb up and over the walls of containers, flow through impossibly tiny cracks, and remain in motion indefinitely once started. It is a quantum phenomenon, a state where the entire fluid behaves as a single quantum entity. Superfluid helium has other strange properties. It conducts heat better than any other known substance, hundreds of times better than copper. It can create fountains that spray upward spontaneously, driven by temperature differences. Watching superfluid helium is surreal, as it seems to violate common sense. The discovery of superfluidity earned several Nobel Prizes and opened new fields of physics. To study superfluids is to explore the quantum realm, where particles behave in ways that classical physics cannot explain. Freezing, taken to its extreme, reveals a universe stranger than we imagine. Bose-Einstein condensates form near absolute zero. At temperatures a fraction above absolute zero, certain atoms can be cooled into a state called a Bose-Einstein condensate. In this state, atoms lose their individual identities and merge into a single quantum entity. Thousands or millions of atoms behave as one, described by a single quantum wave function. It is matter at its most exotic, a state predicted by Albert Einstein and Satyendra Nath Bose in the 1920s but not created until 1995. Creating a Bose-Einstein condensate requires extraordinary cold, often just billionths of a degree above absolute zero. At these temperatures, the quantum properties of atoms, normally negligible, become dominant. The condensate behaves as a single superatom, and studying it reveals fundamental aspects of quantum mechanics. Bose-Einstein condensates have been used to test theories, simulate other quantum systems, and explore the boundary between quantum and classical physics. They are proof that cold is not merely the absence of heat, but a gateway to entirely new forms of matter. Frozen lakes make eerie sounds as ice shifts. In winter, frozen lakes are not silent. As temperatures change, the ice expands and contracts, creating stress. This stress is released suddenly, producing sounds that range from sharp cracks to deep booms. The noises can be startling, like rifle shots or rolling thunder echoing across the ice. Sometimes the ice sings, producing high-pitched tones that resonate and fade. These sounds are caused by the ice fracturing and shifting, vibrations traveling through the solid surface. People walking or skating on frozen lakes sometimes hear these sounds up close, a reminder of the dynamic forces at work beneath their feet. The ice is never truly still. It is bending, flexing, and adjusting to temperature changes. Thick ice is generally safe, but the sounds can be unnerving, especially for those unfamiliar with winter lakes. For those who know them, the sounds are simply winter's voice, the frozen lake speaking as it settles into the cold. Clear ice forms when water freezes slowly. The clarity of ice depends on how it freezes. When water freezes slowly, dissolved gases and impurities have time to escape or migrate, and ice crystals grow in ordered patterns. The result is clear, transparent ice. When water freezes quickly, gases and impurities are trapped, and crystal growth is chaotic. The result is cloudy or white ice, filled with tiny bubbles and imperfections. Clear ice is prized for its beauty and is used in sculptures and premium cocktails. Making clear ice at home is possible, but requires patience. Water must be frozen slowly, often from one direction, allowing gases to escape. Some methods involve insulating the sides and top of the container, so ice forms from the bottom up. The result is crystal clear ice that refracts light beautifully. In nature, clear ice forms on lakes when conditions are calm and temperatures drop gradually. The ice becomes a window into the water below, sometimes so transparent that it is difficult to tell where the surface is. Ice sculptures are carved from clear ice blocks. Ice carving is an ancient art, transforming blocks of ice into intricate sculptures. Artists use chainsaws, chisels, and heated tools to shape the ice, working quickly before it melts. Competitions draw sculptors from around the world, creating everything from realistic animals to abstract forms. The beauty of ice sculptures lies partly in their transparency and the way they interact with light. They glow when illuminated, and their smooth surfaces reflect and refract light in mesmerizing ways. Ice sculpture has practical challenges. The material is cold, slippery, and brittle. Artists must work with the grain of the ice, understanding how it will fracture. Detailed work is difficult because fine features are fragile and prone to breaking. Yet skilled sculptors create astonishing works, some standing several meters tall and weighing tons. Ice sculptures are temporary, melting within hours or days depending on temperature. This impermanence is part of their appeal, a reminder that beauty need not last forever to be meaningful. Ice hotels are built entirely from snow and ice. In Sweden, Canada, and other cold regions, hotels are constructed each winter entirely from ice and snow. These ice hotels feature rooms, furniture, and decorations, all carved from frozen water. Beds are blocks of ice covered with insulating materials and furs. Walls are sculpted with intricate designs, and colored lights create atmospheric glows. Temperatures inside remain below freezing, so guests sleep in thermal sleeping bags designed for extreme cold. Building an ice hotel requires tons of ice and snow, harvested from nearby rivers or manufactured using snow cannons. Artists and builders work for months to create the structure, which stands only for the winter season. When spring arrives, the hotel melts, returning its water to the earth. Each year, the design is different, making each season's hotel unique. Staying in an ice hotel is a surreal experience. Sleeping surrounded by ice in rooms that feel both raw and refined. Temporary shelters in the heart of winter. Icicles form when melting water refreezes. Icicles hang from roofs, branches, and cliffs, formed when water drips and refreezes. The process begins with melting, often caused by sunlight warming a surface, or heat escaping through a roof. Water runs downward and drips off an edge. When the drip enters colder air, it freezes before it can fall. Additional water flows down, adding to the icicle, which grows longer and thicker. The classic icicle shape, narrow at the tip and wider at the base, results from the physics of freezing and water flow. Icicles can grow impressively large, hanging several meters long in the right conditions. They are also dangerous, as their weight can cause them to fall without warning, potentially causing injury. Icicles on roofs often indicate ice dams, where melting snow refreezes at the roof's edge, trapping water and potentially damaging the structure. Despite the hazards, icicles are beautiful, catching light and glittering like natural crystals. They are winter's jewelry, delicate and cold, hanging silent until they melt or fall. Frozen waterfalls create ice climbing challenges. When waterfalls freeze, they become vertical playgrounds for ice climbers. Frozen waterfalls form when temperatures stay below freezing long enough for the flowing water to ice over, layer by layer. The result is a cascade of ice, sometimes hollow, sometimes solid, textured with frozen spray and icicles. Ice climbers use specialized equipment, ice axes and crampons, to ascend these formations, driving tools into the ice to support their weight. Ice climbing is dangerous and demanding. The ice can be unpredictable, fracturing or collapsing under stress. Conditions change constantly, temperatures fluctuating and altering the ice's stability. Yet the challenge attracts climbers worldwide, drawn by the beauty and the test of skill. Climbing a frozen waterfall is an intimate encounter with ice, feeling its texture, testing its strength, trusting your tools and technique. When successful, the reward is reaching the top and looking back at the glittering column you ascended. Frozen water transformed into a vertical challenge. Glaciers contain most of Earth's fresh water. The vast majority of Earth's fresh water, about 70%, is frozen in glaciers and ice sheets. Antarctica alone holds enough ice to raise global sea levels by nearly 60 meters if it all melted. Greenland's ice sheet contains enough for another 7 meters. These massive reservoirs of ice accumulated over millennia, snow falling year after year, compressing into ice kilometers thick. They are planetary archives, recording climate history and vital resources, potentially supplying fresh water to future generations. The amount of ice on Earth is staggering, measured in millions of cubic kilometers. Yet, it is not static. Glaciers are shrinking worldwide, losing mass as temperatures rise. The ice that took thousands of years to accumulate is melting in decades. This loss affects sea levels, ocean currents, and fresh water availability. The fate of glaciers is tied to the global climate, and their future will shape the world's coastlines and ecosystems. To stand on a glacier is to stand on one of Earth's great reservoirs, frozen water held in suspended time, now flowing back into the seas. Ice ages have shaped Earth's history. Earth has experienced multiple ice ages, periods when global temperatures dropped and ice sheets expanded across continents. The most recent, the Pleistocene Ice Age, lasted from about 2.6 million years ago until roughly 11,000 years ago. During its coldest phases, ice covered much of North America, Europe, and Asia. Sea levels dropped as water was locked in glaciers, exposing land bridges like the one between Asia and North America that early humans crossed to reach the Americas. Ice ages are driven by changes in Earth's orbit and tilt, known as Milankovitch cycles, which alter the amount of solar radiation reaching different parts of the planet. These cycles trigger feedback mechanisms. Ice reflects sunlight, cooling the planet further, and changes in carbon dioxide levels amplify the warming or cooling. The cycle of ice ages and warmer interglacial periods is written in ice cores, ocean sediments, and the landscapes carved by ancient glaciers. We currently live in an interglacial period, but geological history suggests that ice ages will return, though the timescale is tens of thousands of years. Snowball Earth froze the entire planet. Around 700 million years ago, Earth may have experienced the most extreme freezing event in its history. Snowball Earth. Geological evidence suggests that the entire planet, from pole to equator, was covered in ice. Glacial deposits from this period are found in locations that were near the equator at the time. The ice may have been several kilometers thick in places, and global temperatures plunged. The planet became a frozen wasteland, inhospitable and alien. How Earth escaped this frozen state is debated. Volcanic eruptions likely continued beneath the ice, slowly releasing carbon dioxide into the atmosphere. Without liquid oceans to absorb it, carbon dioxide accumulated until greenhouse warming became strong enough to melt the ice. The thaw would have been dramatic, swinging from extreme cold to extreme heat. Remarkably, life survived Snowball Earth, sheltering in isolated refuges, perhaps near volcanic vents or in ice-free pockets. The event may have even spurred evolutionary innovation, as surviving organisms adapted and diversified in the aftermath. Snowball Earth is a reminder of how extreme Earth's climate can become and how resilient life is. Antarctica is the coldest place on Earth. Antarctica holds the record for the coldest temperature ever recorded on Earth's surface, -89.2 degrees Celsius, measured at Vostok Station in 1983. More recently, satellite data detected even colder temperatures, reaching -94 degrees Celsius in pockets of the Antarctic plateau. These extremes occur during the polar night, when the sun does not rise for months. The ice surface radiates heat into space, and in calm, clear conditions, temperatures plummet. Living at these temperatures is nearly impossible. Exposed skin freezes in seconds, metal becomes brittle and shatters, fuel gels and machinery fails. Even breathing is painful, as the frigid air shocks the lungs. Yet researchers endure these conditions, staffing Antarctic stations year-round to study climate, ice, and the universe. Antarctica is a natural laboratory, its extreme cold and isolation offering insights available nowhere else. The continent is also stunningly beautiful, a landscape of ice and rock, untouched by most of humanity, a frozen frontier at the bottom of the world. The Arctic Ocean freezes over each winter. The Arctic Ocean is covered by sea ice that expands each winter and contracts each summer. At its maximum extent in late winter, the ice covers about 15 million square kilometers, an area larger than Antarctica's landmass. In summer, the ice retreats, sometimes to as little as 4 to 5 million square kilometers. This seasonal cycle is driven by temperature and sunlight, with the Arctic experiencing continuous darkness in winter and continuous daylight in summer. Arctic sea ice is thinning and declining. Observations show that the summer minimum extent has decreased dramatically over recent decades, and the ice that remains is younger and thinner. The loss of Arctic sea ice has global implications, affecting weather patterns, ocean currents, and ecosystems. Polar bears, seals, and other species depend on sea ice for hunting and breeding. For indigenous Arctic communities, the ice is part of their way of life, used for travel and hunting. The changing ice is a visible indicator of a warming climate, a frozen world in retreat. Polar night lasts months in the high Arctic. At latitudes above the Arctic and Antarctic circles, the sun does not rise for part of the year. This period of continuous darkness is called polar night, and its duration increases closer to the poles. At the North Pole itself, polar night lasts about 6 months. During this time, temperatures plummet, and the landscape is illuminated only by moonlight, starlight, and the occasional aurora. The darkness is profound, a winter that seems endless. For people living through polar night, the lack of sunlight affects mood, sleep, and health. Seasonal affective disorder is common, and communities adapt with artificial lighting and social activities. Yet there is also beauty in the darkness. The stars are brilliantly clear, and auroras dance across the sky in displays that can last for hours. When the sun finally returns, the event is celebrated, a moment of profound joy as light returns to the frozen world. Polar night is a reminder of Earth's tilt, a seasonal rhythm taken to its extreme. Midnight sun brings continuous daylight in summer. The flip side of polar night is midnight sun, the phenomenon where the sun remains above the horizon for 24 hours. This occurs during summer in polar regions, when the Earth's tilt directs continuous sunlight toward the poles. At the North and South poles, the sun circles the horizon, never setting for about 6 months. The constant daylight is disorienting, disrupting normal sleep patterns and creating surreal landscapes bathed in eternal twilight. Plants and animals in polar regions have adapted to these extremes. Arctic flowers bloom rapidly during the brief summer, taking advantage of the continuous light. Migratory birds arrive to breed, feeding almost constantly in the extended daylight. For humans, midnight sun can be exhilarating or exhausting. Some find the energy to work and explore at all hours, while others struggle with insomnia. Blackout curtains become essential for sleep. The midnight sun is a symbol of summer's return, a time of warmth and life in regions defined by their cold. Frost-free days determine growing seasons. In agriculture, the growing season is defined by frost-free days, the period between the last spring frost and the first autumn frost. During this window, temperatures remain above freezing, allowing crops to grow without damage. The length of the frost-free season varies dramatically by latitude and climate. Near the equator, there may be no frost at all, enabling year-round cultivation. In temperate regions, the frost-free period ranges from a few months to more than half the year. In subarctic zones, it may last only a few weeks. Farmers plan their planting and harvesting around frost dates. A late spring frost or early autumn frost can devastate crops, killing tender plants before they mature. Frost protection methods, such as covering plants or using heaters and wind machines, can extend the growing season slightly, but they are costly. Climate change is altering frost patterns in many regions, with later first frosts and earlier last frosts extending growing seasons. This shift has benefits, but also disrupts ecosystems and traditional farming cycles. The simple act of water freezing or not determines what can grow and where, shaping agriculture worldwide. Permafrost affects half of Russia and Canada. Permafrost underlies vast areas of the high northern latitudes, covering about 24% of the northern hemisphere's land surface. In Russia and Canada, permafrost affects more than half the land area, creating unique challenges for infrastructure and ecosystems. Building on permafrost is difficult because any heat from structures can thaw the ground, causing foundations to sink or collapse. Roads buckle, pipelines shift, and buildings tilt as the frozen ground beneath them melts. Engineering solutions for permafrost include building on stilts to allow cold air to circulate beneath structures, using insulated foundations, and even artificially freezing the ground with refrigeration systems. Despite these efforts, warming temperatures are making permafrost less stable. In some areas, the ground is thawing for the first time in millennia, transforming landscapes and releasing stored carbon. Permafrost defines life in the Arctic, shaping where people live, how they build, and what the land can support. It is frozen ground, but it is not permanent. A reminder that even the most stable-seeming systems can change. Frost fairs were held on the frozen Thames during the Little Ice Age, a period of cooler temperatures from the 14th to 19th centuries. The River Thames in London froze solid several times. These events were rare but celebrated with frost fairs, festivals held on the ice. Londoners set up markets, roasted animals, played games, and even printed commemorative souvenirs on presses set up on the frozen river. The ice was thick enough to support tents, fires, and crowds, a temporary carnival on a river that normally flowed. The last Frost Fair was held in 1814. Since then, the Thames has not frozen solid, partly due to changes in the river. Old London Bridge created slower currents that allowed ice to form, but also due to warming temperatures. The frost fairs are a historical curiosity, a reminder that climate is not static and that humans adapt and celebrate even in harsh conditions. To imagine a frozen Thames, bustling with life and laughter, is to glimpse a world where winter was both harsher and more embraced, a season for gathering rather than retreating. Refrigeration changed human society. The invention of mechanical refrigeration in the 19th century transformed civilization. Before refrigeration, preserving food meant salting, smoking, drying, or storing in ice houses. These methods were limited, and food spoilage was a constant problem. Refrigeration allowed food to be kept fresh for weeks or months, reducing waste and enabling the transport of perishables over long distances. Meat, dairy, fruits, and vegetables could be shipped from farms to cities, from one continent to another. Refrigeration also changed where and how people lived. No longer dependent on local food sources, populations could grow in areas without easy access to fresh food. The technology spurred the growth of the frozen food industry, transforming diets and economies. Home refrigerators became common in the 20th century, fundamentally altering daily life. Shopping habits changed, as people could store food at home rather than buying daily. Refrigeration is so ubiquitous now that it is easy to forget how revolutionary it was, a technology that uses controlled freezing to reshape society. Air conditioning uses refrigeration to cool air. Air conditioning is essentially refrigeration applied to air. The system uses the same principles. A refrigerant absorbs heat from indoor air and releases it outside, cooling the interior. The invention of modern air conditioning in the early 20th century made living and working in hot climates far more comfortable. It enabled the growth of cities in regions that were previously too hot for large populations. The southern United States, the Middle East, and tropical cities all expanded rapidly after air conditioning became widespread. Air conditioning transformed architecture, allowing buildings to be sealed with glass and designed without natural ventilation. It changed work patterns, enabling factories and offices to operate efficiently, regardless of heat. It also changed culture, as people spent more time indoors in climate-controlled environments. Yet air conditioning is energy-intensive and contributes to climate change through electricity use and refrigerant leakage. The irony is that cooling buildings warms the planet. Air conditioning is a comfort born of controlled freezing, but it comes with costs that societies are only beginning to fully reckon with. Freeze-thaw cycles crack and break materials. The expansion of freezing water is not just a natural process, but a destructive force on human infrastructure. Freeze-thaw cycles occur when water seeps into cracks in concrete, asphalt, or stone, then freezes and expands. The pressure widens the crack. When the ice melts, more water enters, and the cycle repeats. Over time, small cracks become large fissures, and solid materials break apart. This is why potholes are so common in regions with freezing winters. Buildings, bridges, and dams all suffer from freeze-thaw damage. Engineers design structures to minimize water infiltration and use materials resistant to cracking, but the process is relentless. In mountainous regions, freeze-thaw cycles contribute to rockfalls and landslides. Ancient ruins in cold climates show the scars of centuries of freezing and thawing. Stones split and crumbled by ice. The power of freezing water is patient but unstoppable, working year after year to dismantle even the most solid structures. Frost forms patterns that follow physics. The patterns that frost creates on windows and surfaces are not random, but follow the laws of physics. Ice crystals nucleate at certain points and grow outward, following paths determined by temperature gradients, humidity, and the surface's microscopic structure. The branching patterns resemble ferns or feathers because of dendritic growth, where crystals grow faster in certain directions, creating arms that branch repeatedly. Each pattern is unique, but governed by the same principles. Scientists study frost patterns to understand crystal growth in other contexts, from metallurgy to pharmaceutical manufacturing. The mathematics of pattern formation reveals universal principles that apply across scales, from tiny frost ferns to the structure of galaxies. To see frost on a window is to witness physics at work, invisible forces creating visible beauty. The patterns are temporary, erased by warmth, but they reappear each cold morning, evidence of the order hidden in nature's apparent chaos. Hoarfrost transforms landscapes overnight. Hoarfrost can appear suddenly, transforming a landscape overnight. The conditions must be perfect: clear skies, high humidity, calm air, and temperatures below freezing. When these align, water vapor deposits directly onto surfaces as ice crystals, growing outward in feathery structures. By morning, every tree, fence post, and blade of grass is coated in white, a world made of ice lace. The effect is magical, as if winter has cast a spell overnight. Hoarfrost is fragile, melting quickly when the sun rises or when touched. Walking through a hoarfrost-covered forest feels like trespassing in a frozen dream. The only sound, the crunch of frost underfoot, and the occasional crash of ice falling from branches. Photographers treasure hoarfrost mornings for the beauty and the way the ice catches light. It is a fleeting gift, lasting hours at most, before warmth reclaims the landscape. To witness hoarfrost is to see winter's artistry, nature's delicate touch creating beauty from cold air and moisture. Ice storms can last for days. Some ice storms persist for extended periods, layering ice thicker and thicker. These prolonged events are rare but devastating. Each hour adds more ice, the weight growing until branches, power lines, and structures can no longer bear it. The sound of breaking wood becomes constant, a symphony of destruction. Power outages can last weeks, as utility crews struggle to repair damage across wide areas. Entire communities are paralyzed, isolated by impassable roads and lack of electricity. Recovery from severe ice storms takes months or years. Forests lose large numbers of trees, altering ecosystems and increasing wildfire risk as dead wood accumulates. Farms suffer losses as ice-damaged orchards and infrastructure require rebuilding. Yet even these disasters demonstrate resilience. Communities come together, sharing resources and helping neighbors. Ecosystems adapt, new growth filling gaps left by fallen trees. Ice storms are reminders of nature's power and of the fragility of the systems we depend on, but also of the capacity to rebuild. Glacial ice can be thousands of years old. The ice in glaciers is ancient, Near the surface, the ice may be only years or decades old, but deeper ice can be thousands of years old. In the center of the Antarctic ice sheet, ice at the bottom is over 800,000 years old, deposited as snow in a world vastly different from today. This ice is a time capsule, containing air bubbles from ancient atmospheres, dust from volcanic eruptions, and pollen from plants long extinct in those regions. Scientists drill ice cores to retrieve this ancient ice, analyzing it layer by layer. Each year's snowfall creates a distinct layer, like tree rings, allowing precise dating. The information locked in glacial ice has revolutionized our understanding of Earth's climate history. We can see how carbon dioxide levels have changed, how temperatures have fluctuated, and how abrupt climate shifts can be. To hold a piece of glacial ice is to hold history, frozen water that fell before civilizations rose, preserved in cold silence until brought back into the light. Icebergs can flip without warning. Icebergs float in delicate balance, with most of their mass below water. As they melt unevenly, their center of gravity shifts. If the shift becomes too great, the iceberg can roll suddenly, flipping in the water. This is dangerous for nearby ships and people, as the movement generates waves and the newly exposed underside can be jagged and unstable. Icebergs that have flipped recently show brilliant blue ice, the compressed ancient ice that was formerly deep underwater. The flipping of icebergs is unpredictable. An iceberg that appears stable can roll without warning, especially as melting accelerates. Calving, where chunks break off, can also trigger flipping by, suddenly changing the iceberg's shape and balance. Observers describe the sound as like thunder, the roar of tons of ice rotating and crashing into the sea. To witness an iceberg flip is to see the power and instability of ice, seemingly solid and permanent but always in motion, always changing. Ice floats because of hydrogen bonds. The reason ice floats is rooted in chemistry. Water molecules are polar, with a positive end and a negative end. This polarity allows them to form hydrogen bonds, weak attractions between the hydrogen of one molecule and the oxygen of another. In liquid water, these bonds form and break constantly, allowing molecules to move freely. When water freezes, the molecules arrange themselves into a stable hexagonal lattice, held in place by hydrogen bonds. This structure creates open spaces, making ice less dense than liquid water. Without hydrogen bonding, water would not behave this way. Most substances are denser as solids than liquids because their molecules pack more tightly. Water's unusual behavior is critical for life. If ice sank, aquatic ecosystems would be vastly different, and Earth's climate would be altered. The simple fact that ice floats, determined by the hydrogen bonds between molecules, has shaped the evolution of life and the habitability of our planet. It is molecular geometry with planetary consequences. Supercooled clouds cause ice accretion on aircraft. High-altitude clouds often contain supercooled water droplets, liquid despite being well below freezing. When aircraft fly through these clouds, the droplets freeze instantly on contact with the cold metal surfaces, building up layers of ice. This ice accretion disrupts aerodynamics, adding weight, reducing lift, and potentially causing loss of control. It can block sensors, freeze control surfaces, and even shut down engines if ice is ingested. Modern aircraft have de-icing systems, using heated surfaces, inflatable boots, or chemical sprays to remove or prevent ice buildup. Pilots are trained to avoid icing conditions or exit them quickly. Despite precautions, icing remains a hazard. Several accidents have been caused by ice overcoming anti-icing systems or pilots failing to recognize the severity of icing conditions. Supercooled clouds are invisible threats, their danger revealed only when ice begins to form. The freezing of tiny droplets, happening in instants, can endanger lives and machines. Graupel forms when supercooled droplets freeze on snowflakes. Graupel is a type of precipitation that forms when supercooled water droplets collide with falling snowflakes and freeze on contact. The result is a soft, opaque pellet, larger and denser than a snowflake, but softer than hail. Graupel falls like snow, but bounces when it hits the ground, making a distinctive sound. It is sometimes called soft hail or snow pellets. Graupel often falls in winter storms, mixed with snow or sleet. The formation of graupel requires specific atmospheric conditions, a layer of supercooled droplets and falling ice crystals that collect the droplets as they descend. Graupel is an intermediate between snow and hail, less dramatic than either, but common enough to be familiar to those in snowy climates. It accumulates quickly, covering the ground in small white pellets. Graupel is yet another form of frozen precipitation, a reminder of the many ways water can freeze in the atmosphere. Hail forms through repeated freezing in thunderstorms. Hail is ice that falls from thunderstorms, and its formation involves repeated journeys through different layers of the atmosphere. Hailstones begin as small ice particles or frozen raindrops. Strong updrafts in a thunderstorm carry them upward into regions where supercooled water droplets freeze onto them, adding layers. The growing hailstone falls, then is caught by another updraft and carried up again, accumulating more ice. This cycle can repeat multiple times, building the hailstone layer by layer. Cutting a hailstone in half reveals its history. Concentric layers of ice, like an onion. Each layer represents a trip through the storm. The largest hailstones, some as big as grapefruits, have made many such journeys, accumulating ice over tens of minutes. Hail is destructive, shattering windows, damaging crops, denting vehicles, and occasionally injuring or killing people and animals. It falls at high speeds, driven by gravity and the winds of the storm. To see hail fall is to witness the violence of thunderstorms, ice created by extreme atmospheric forces. Freezing point depression allows salt to melt ice. Salt lowers the freezing point of water, a phenomenon called freezing point depression. Pure water freezes at 0 degrees Celsius, but when salt is dissolved in water, the freezing point drops. This is why salt is spread on roads and sidewalks in winter. The salt dissolves in the thin layer of liquid water on ice, lowering its freezing point so the ice melts even at temperatures below 0. The effectiveness depends on the temperature. Salt works well down to about -10 degrees Celsius, below which other chemicals are needed. Freezing point depression is a colligative property, meaning it depends on the number of dissolved particles, not their type. Other substances, like sugar or antifreeze, also lower the freezing point. This principle has practical applications beyond de-icing. It is why seawater resists freezing, and why animals in cold environments produce antifreeze compounds in their blood. Freezing point depression is chemistry at work, a simple concept with widespread implications. From winter road safety to the survival of Arctic fish, antifreeze proteins protect fish in polar oceans. Some fish living in polar waters produce antifreeze proteins that prevent their blood from freezing. These proteins bind to tiny ice crystals that form in the blood and prevent them from growing larger. The fish's blood can remain liquid even at temperatures below the normal freezing point of seawater, which is around -2 degrees Celsius. Without these proteins, ice crystals would form and rupture cells, killing the fish. Antifreeze proteins are a remarkable evolutionary adaptation. They have independently evolved in several unrelated groups of fish, demonstrating convergent evolution. The proteins work by disrupting the normal crystal structure of ice, effectively lowering the freezing point of the fish's body fluids. Scientists study these proteins for potential applications, from improving frozen food preservation to protecting transplant organs during storage. Antifreeze proteins are proof of life's ingenuity, molecular solutions to the problem of cold, allowing fish to thrive in oceans that would otherwise be uninhabitable. Frost flowers form on young sea ice. Frost flowers are one of nature's most delicate ice formations. They grow on newly formed sea ice when extremely cold air comes into contact with the ice surface. Water vapor sublimates from the ice, or from brine channels in the ice, then freezes immediately into intricate ice crystals that build upward and outward. The result looks like tiny bouquets of white flowers scattered across the ice. Frost flowers are fragile, collapsing at the slightest touch or gust of wind. Frost flowers contain high concentrations of sea salt and organic material rejected from the ice as it formed. They can support microbial life, creating tiny ecosystems in one of Earth's harshest environments. When broken by wind, frost flower fragments become aerosols that can travel long distances and influence cloud formation. Despite their beauty and scientific interest, frost flowers are ephemeral, lasting only hours or days. They are nature's most fleeting ice sculptures, blooming briefly on the frozen sea before vanishing. Diamond dust is tiny ice crystals suspended in air. On extremely cold, clear days, the air itself can seem to sparkle. This is diamond dust, a phenomenon where tiny ice crystals form in the air and remain suspended. The crystals are so small and light that they fall very slowly, creating a glittering haze. Diamond dust occurs in polar regions and high mountains, when temperatures are well below freezing and the air is very still. Water vapor freezes directly into ice, forming microscopic crystals that catch and reflect sunlight. Walking through diamond dust is magical. The air shimmers with light, and every breath reveals more crystals suspended around you. Sunlight passing through the crystals can create halos and light pillars, atmospheric optical effects that add to the otherworldly beauty. Diamond dust is harmless, unlike snow or ice storms, but it signals severe cold. It is winter's gentlest form, frozen air sparkling in silence, a reminder that even the harshest environments have moments of quiet beauty. Sundogs are created by ice crystals. Sundogs, or parhelia, are bright spots that appear on either side of the sun, often with a halo connecting them. They are caused by sunlight refracting through hexagonal ice crystals in high, cold clouds. The crystals act like prisms, bending light and creating these brilliant spots. Sundogs are most vivid when the sun is low on the horizon and the ice crystals are oriented horizontally, aligned by gentle air currents. Sundogs have been observed and recorded for millennia, often interpreted as omens or divine signs. They are most common in winter and in polar regions, where ice crystal clouds are frequent. Sometimes they are accompanied by other phenomena, halos, arcs, and pillars, all created by light interacting with ice. Sundogs are a reminder that ice shapes not only the physical world, but also the light passing through it, bending and refracting rays into beauty. To see sundogs is to witness light frozen, transformed by crystals into spectacle. Light pillars are reflections from floating ice crystals. Light pillars are vertical shafts of light that extend above or below bright light sources. They occur when flat ice crystals fall slowly through the air, their faces horizontal. The crystals act like mirrors, reflecting light from the sun, moon, or artificial lights. The result is a pillar of light extending upward, sometimes for hundreds of meters. Light pillars are most common in winter during cold, calm nights with ice crystal fog. Seeing a light pillar can be startling. A column of light hovering in the sky with no apparent source. They are purely optical phenomena, not real objects, and they appear in different places to different observers. Light pillars are delicate, requiring precise conditions of crystal orientation and light angle. They are yet another way ice interacts with light, creating illusions that inspire wonder. To see a city's streetlights transformed into glowing pillars reaching into the night is to witness ice's artistry. Freezing rain is more dangerous than snow. Freezing rain causes more hazardous conditions than snow. While snow accumulates and can be plowed or driven on carefully, freezing rain creates smooth, glassy ice that is nearly impossible to walk or drive on safely. It coats everything uniformly, turning surfaces into skating rinks. Trees and power lines are particularly vulnerable, as the weight of ice accumulates until branches and wires snap. A severe freezing rain event can shut down entire regions, causing more damage than heavy snowstorms. The danger of freezing rain is its invisibility until too late. Rain appears normal, but surfaces are at or below freezing. The first sign is often loss of traction, vehicles sliding or pedestrians falling. Once ice has formed, removal is difficult. Salt is less effective on thick ice, and mechanical removal can damage surfaces. Freezing rain is a winter hazard that demands respect, a reminder that water's transition to ice can happen instantly and with devastating consequences. Ice roads connect remote communities. In regions with long, cold winters, frozen lakes and rivers become highways. Ice roads are temporary routes used to transport goods and people across areas with no permanent roads. In northern Canada, ice roads connect remote communities and mining operations, providing access for only a few months each year. Trucks carry heavy loads across the ice, relying on thickness measurements and experience to determine safe routes and weight limits. Building and maintaining ice roads requires expertise. The ice must be thick enough to support heavy vehicles, typically at least 70 centimeters for large trucks. Too early or too late in the season, the ice is unsafe. Engineers sometimes flood the ice to add layers or plow snow off to allow thicker ice to form. Ice roads are vital lifelines, bringing fuel, food, and supplies to places unreachable by other means. They are also inherently dangerous, with vehicles occasionally breaking through thin ice. Ice roads are infrastructure born of freezing, temporary bridges that exist only when water becomes solid. The polar vortex is a swirl of cold air. The polar vortex is a large area of low pressure and cold air surrounding the Earth's poles. It exists year-round, but strengthens in winter. Normally, strong winds called the jet stream keep this cold air confined near the poles, but sometimes the vortex weakens or becomes distorted, allowing frigid Arctic air to spill southward into lower latitudes. When this happens, regions that normally have mild winters can experience extreme cold and heavy snow. Polar vortex events have become more frequent in recent years, though the reasons are debated. Some scientists link them to changes in Arctic sea ice and atmospheric circulation. During a polar vortex event, temperatures can plunge by 20 or 30 degrees in a matter of hours. The cold can be dangerous, causing frostbite in minutes and overwhelming heating systems. The polar vortex is not a storm, but a pattern, a shift in atmospheric flow that brings the deep cold of the Arctic to places unaccustomed to it, a reminder that winter's reach can extend far beyond its usual domain. Crevasses, form, where glaciers crack under stress. As glaciers flow over uneven terrain, they bend and stretch, creating stresses in the ice. Where these stresses exceed the ice's strength, it cracks, forming crevasses. These are deep fissures in the glacier's surface, sometimes tens of meters deep and several meters wide. Crevasses can be hidden under snow bridges, thin layers of snow that conceal the void below. They are deadly hazards for anyone traveling on glaciers. Crevasses form in predictable patterns based on the glacier's topography and flow. Transverse crevasses form perpendicular to the flow direction, while longitudinal crevasses run parallel. Where glaciers turn or flow around obstacles, complex networks of crevasses can form, creating ice mazes. Climbers and glaciologists use ropes and probes to navigate crevasse fields safely. Falling into a crevasse is a serious danger, as the walls are sheer ice, and escape without help is nearly impossible. Crevasses are wounds in the glacier, evidence of the immense forces at work as ice slowly flows downhill. Moulins funnel meltwater into glaciers. On the surface of glaciers, meltwater streams flow across the ice. Sometimes these streams encounter a weak point, a crack or crevasse, and plunge downward into the glacier. These vertical shafts are called moulins, from the French word for mill, because the swirling water resembles a mill wheel. Moulins can be tens of meters deep, draining surface meltwater to the base of the glacier where it flows beneath the ice. Moulins are dangerous to approach. The water flows fast, and the edge of the hole can be unstable. Scientists study moulins to understand how meltwater affects glacier flow. Water reaching the glacier's base acts as a lubricant, allowing the ice to slide faster over bedrock. In a warming climate, increased surface melting creates more moulins, potentially accelerating glacial flow and retreat. Moulins are portals into the glacier's interior, revealing that glaciers are not solid blocks, but dynamic systems with internal flows and hidden rivers of meltwater. Glacial lakes form behind ice dams. Sometimes glaciers block valleys, creating natural dams. Water accumulates behind these dams, forming glacial lakes. These lakes can grow large, holding millions of cubic meters of water. The ice dam is unstable, however. As the glacier melts or shifts, the dam can fail suddenly, releasing the lake in a catastrophic flood called a glacial lake outburst flood, or GLOF. These floods are among the most destructive natural disasters, sending walls of water, ice, and debris rushing down valleys. GLOFs have destroyed villages, washed away bridges, and altered landscapes. In the Himalayas, where glacial lakes are common, the risk is increasing as glaciers retreat and new lakes form. Monitoring these lakes and installing early warning systems are ongoing challenges. GLOFs are reminders that ice is not static. The dams holding back these lakes are temporary, and their failure can unleash frozen water's power in sudden, violent release. The lakes themselves are beautiful, turquoise or milky blue, cradled in valleys beneath towering ice, yet they hold latent danger. And so, we come to the end. Dear listener, our journey through the world of freezing comes to a close. From the smallest ice crystal to the vast glaciers covering continents, from the delicate frost on a window to the powerful forces reshaping landscapes, we have explored the many forms and faces of frozen water. We have seen how freezing preserves life, threatens it, creates beauty, and shapes the very ground beneath our feet. Freezing is not merely the absence of warmth, but a dynamic process, a transformation that occurs at every scale, from molecules to planets. As you lie here, breathing slowly and letting your thoughts drift, imagine yourself in a winter landscape. Perhaps you are in a snowy forest, each branch coated in hoarfrost, the air crisp and still. Or maybe you stand on the edge of a frozen lake, the ice beneath you thick and solid, the surface polished smooth by wind. Above you, the night sky shimmers with auroras, curtains of green and purple light rippling across the stars. The cold is all around, but you are warm, protected, at peace. Picture the slow formation of a snowflake high in the atmosphere. A single water molecule deposits onto a microscopic nucleus, then another molecule, and another. The crystal grows, branching outward in six-fold symmetry, each arm elaborated with fine details determined by temperature and humidity. After perhaps 20 minutes, the snowflake is complete, unique in all the world, and it begins its slow descent to Earth. You watch it fall, spinning gently through the air, catching light, until it lands softly on the ground and joins billions of others, becoming part of the blanket that insulates and transforms the landscape. Freezing is everywhere, and always. It is the frost forming on your window tonight, the ice cubes in your freezer, the distant glaciers flowing toward the sea. It is the supercooled droplets in clouds waiting to freeze, the permafrost beneath tundra holding ancient carbon, the ice cores being drilled in Antarctica to unlock climate secrets. Freezing is both intimate and immense, a process as personal as the cold on your skin and as vast as ice ages that reshaped continents. In this moment, you are here, comfortable and safe, your body relaxing more deeply with each breath. The world outside may be cold or warm, but here you are at rest. Let the images of frozen water drift through your mind. Icicles hanging from eaves, catching afternoon sun. Snow falling silently in a dark forest. Ice crystals forming patterns on a window. A glacier carving into the sea. The thunder of falling ice echoing across the water. These images require no effort. They simply are, like the gentle rhythm of your breathing, like the slow descent into sleep. Freezing teaches us patience. Ice forms slowly, molecule by molecule. Glaciers flow at the pace of seasons and centuries. Frost appears overnight, but follows patterns written in physics. There is no rush. There is only the steady accumulation, the gradual transformation, the quiet work of cold. As you sink deeper into rest, let yourself be like water freezing, finding stillness, releasing motion, settling into structure. There is safety in this. There is peace. The night is long, and you have all the time you need. There is nothing to do, nowhere to go, just the soft embrace of blankets, the weight of your body sinking into the mattress, the gentle slowing of your thoughts. Outside, the world continues, but here, in this moment, you are suspended, held in warmth while contemplating cold, present while drifting toward dreams. Imagine the silence of a snow-covered field at night. The snow muffles every sound, absorbing noise and leaving only quiet. The sky above is clear, stars brilliant and sharp in the cold air. Your breath rises in small clouds, visible for a moment before disappearing. You are alone, but not lonely. The stillness is companionable. The cold, a presence rather than a threat. Everything is soft edges and gentle light, reflected from snow to sky and back again. The world is simplified, reduced to essentials: earth, sky, cold, light. It is beautiful in its starkness. As you lie here, feel the softness of your pillow, the warmth of your blankets. Notice how your muscles have relaxed, how your breathing has deepened. There is no tension left, only the gentle weight of rest. Your mind, which has traveled through ice caves and across frozen oceans, through snowflakes and glaciers, is now ready to release even these images. Let them fade like frost in morning sun. Let them melt into the background, becoming merely a gentle presence, a lingering sense of winter's peace. Freezing is transformation, and sleep is transformation too. The boundary between waking and sleeping is like the boundary between water and ice, a threshold crossed gradually, almost imperceptibly. You are crossing that threshold now, gently, easily, without effort. The journey has been long, and you have traveled far, but now you are arriving at rest, arriving at silence, arriving at sleep. If you happen to still be awake, you can let these final words wash over you like falling snow, each one settling softly, building into a quiet blanket. But if your eyes have closed, if your thoughts have drifted into dreams, then let them carry you. Let the images of frozen water, of ice and snow, of winter's stillness become the backdrop for your dreams. Let the cold become comfort, the winter become welcome. Breathe in, breathe out. Feel yourself sinking deeper, colder in the best way, frozen into stillness, preserved in peace. The night holds you, the darkness is gentle. And in this moment, surrounded by warmth, while thinking of cold, you are exactly where you need to be. Good night. Sleep well. Let the frozen world hold you in its quiet embrace until morning light returns.